Positive electric charge Q is distributed uniformly along a line with length 2a, lying along the y-axis between y equals negative a and y equals positive a. Find the electric field at point P on the x-axis at a distance x from the origin. X is the distance from the line to the location of our test charge P. dq is a tiny amount of charge contained in a tiny section of the line dy. Y is the distance from where x touches the line to dq. R is the distance from dq to the location of the test charge P. Alpha is the angle between x and r. So coming from the formula of electric field due to point charge, we can derive a formula for this problem. The charge has electric field in both x and y axis, so we need to solve it. The angle in the electric field of x axis is equal to cosine phi, while the angle in the y axis has sine phi. So we substitute our values we got from the angle. The derivative of electric field in the x axis is equal to x times k times q, as the derivative of y over 2a times x squared plus y squared over 3 halves. And the derivative of x electric field in the y-axis is equal to the negative y times k times q, as the derivative of y over 2a times x squared plus y squared to the power 3 halves. So we expand the equation more by integrating it. Put the constants outside the integration so we can have a small equation to integrate. So the electric field in the x-axis is equal to k times q times x over 2a times the integration of dy over 2a times x squared plus y squared to the 3 halves from negative a to a. So the electric field in the y-axis is equal to negative k times q times over 2a times the integration of y dy over 2a times x squared plus y squared to the 3 halves from negative a to a. The electric field in the y-axis is equal to negative kq over 2a times the integration of y dy over the quantity of x squared plus y squared raised to 3 halves from negative a to positive a. This is equal to negative 1 over square root of x squared plus y squared minus negative 1 over square root of x squared plus y squared. Now, negative 1 minus negative 1 is equals to 0. Since this is a subtraction, both fractions must have the same denominator. So, the final answer for the electric field in the y-axis is equal to 0. The electric field in the x-axis is equal to kq over 2a times the integration of dy over the quantity of x squared plus y squared raised to 3 halves from negative a to positive a. This is equal to a over x squared times the square root of x squared plus a squared minus negative a over x squared times the square root of x squared plus a squared. Now, a positive a minus negative a will give us 2a, and again, since this is a subtraction, both fractions must have the same denominator. Simplifying further will give us the electric field in the x-axis, which is equal to kq over x times the square root of x squared plus y squared. This is called the finite line of charge, where you are to find the electric field in a long or short wire. If we assume that a is greater than x or a approaches infinity, we can also get another formula. By multiplying 1 over a in the equation of the line of charge, we can cancel a in the numerator. We can divide 1 over a because of the process called rationalization. A rule in solving for radicals, but in this example, we simply reverse the process so that we can have 1 over a at the denominator. Since 1 over a is equal to the square root of 1 over a squared, we can put 1 over a squared inside the square root after you put 1 over a squared inside the square root. Distribute it to the terms, we can cancel out a squared over a squared. Remember that we are assuming that a approaches infinity, so we have to find its limit. Since the limit of x squared over a squared as a approaches infinity is equals to 0. We can have the equation of the electric field in the x-axis as k lambda 2 over x times the square root of 0 plus 1, which is equal to k lambda 2 over x. We can have this as equation, but since k is equal to 1/4 pi epsilon naught, we can simplify it further. So cancel out 2, which leaves us with the equation of the electric field in the x-axis is equal to lambda over 2 pi times epsilon naught times x. This equation is called the infinite line of charge, where you are to the electric field in a very long wire. Note that using the second equation where k is simplified will be more accurate than the other, because k has a constant value of 9 times 10 to the 9th power. Try using the two formulas in the second problem at the end of this part. A long rod has a length of 6 meters. A is only the half of length, so we must divide 6 by 2, which gives us 3 meters. Another given would be the charge that has value of positive 200 nanocoulomb. Lastly would be the distance of the charge from the rod, which is equal to 0.2 meters. So using our formula, from the finite line of charge, we must substitute its value, then have a final answer of 1486.84 nanocoulomb. The linear charge density of the rod is equal to the charge over its length, so we substitute the value and get a final answer of 3.33 times 10 to the negative 8 coulombs per meter. We are given a linear charge density of the rod and the distance of the charge from the rod. So using our formula in the infinity line of charge, we substitute the value of the variables and get a final answer of 4314.02 nanocoulomb.